Hello, my name is Saif Abdulazim. Today I will be presenting a hybrid medical diagnostic expert system that me and Abu Bakr Osama created using machine learning and computer vision for our knowledge engineering course at the American University in Cairo. So let's start with our problem. Early detection of diseases is absolutely crucial to improve patient outcomes. Figuring out whether a patient has cancer or not, or what type of cancer that they have is very, very beneficial for a patient when it comes to detecting and handling whatever the disease might be. So for that effort, me and Abu Bakr, we set out to create a hybrid diagnostic system that is able to predict either whether breast cancer or brain cancer exists or what kind of the brain cancer might be. Okay. So the objective was to create a hybrid system that allows the user to first pick a diagnostic model, whether it's the breast cancer detection or the brain cancer detection system, right? The user is able to enter some medical data or uploaded MRI images, and then they are able to receive AI-assisted diagnostic predictions. The system combines machine learning, computer vision, and just general knowledge engineering concepts to bring our vision to real life. So why do we consider this an expert system? So we have some of the basic components of an expert system. First, we have a knowledge base. The knowledge base comes through our trained machine learning and convoluted neural network models, right? And then we have an inference mechanism where a prediction is being made based on logic and rules that we have created for these trained systems or models. We have a simple user interface. The model is selected by the user, and then they are able to input data on the interface in order to get some results out. And then we have the explanation component where a prediction or an outcome is given. So simply put, knowledge base, inference, and outcome. So input, rules, outcome. This makes this an expert system in our eyes. Yeah, that's it. We have a very simple workflow, as I've been mentioning. So the user is able to open a system and they are able to manually pick whether they want a breast cancer prediction or a brain tumor detection. And then the user provides the text for brain cancer, or they provide images, MRI images for the brain cancer. The selected model processes the input, and then the prediction result is displayed out to the user. Yeah, I don't think we need to talk too much about the system architecture. We're using logistic regression for breast cancer, and we're using a convoluted neural network for the brain tumor. And then we just have input and output layers. There's not too much really to speak on here. Some of the technologies we've used, so obviously we've used Python because we're working with neural networks and logistic regression. We have HTML, CSS, JavaScript that helps us with the general interface and how it works in the backend with the neural networks that we've used. Yeah, and then we use a bunch of different Panda library, Python libraries such as Pandas or NumPy or JobLib to help us get where we need to go. We're using two data sets for this. We have a breast cancer data set. This it's a structured medical. It brings structured medical attributes. And there's obviously cleaning in order to make the data usable for our modules. So the breast cancer module either detects benign or malignant, while the brain tumor data set shows a bunch of pictures that show either a glioma, a meningioma, a pituitary tumor, or no tumor at all. Okay. So as I mentioned, for the breast cancer model, we're using logistic regression. The reason for this is because we're only looking at a binary outcome. It's either malignant or it's either benign. So it's simple, it's interpretable, and it's very effective for something that only gives out a binary output. Yeah, so this makes it very easy. For the brain tumor model, however, we used a convoluted neural network because we have multiple convolution layers, right? And we have activation functions. Um, we want all of these layers to be fully connected so we can have a softmax classification happening. So the input is usually an image, and then computer vision is used to look at these, and then it outputs whether it's a glioma, meningioma, no tumor, or whatever it might be. Right. We've talked about the knowledge engineering concepts that we use. We have encoded medical knowledge inside trained models. So our knowledge is represented in a knowledge-based fashion. The inference that we have happens through predictions that are generated by these trained AI models, whether it's the logistic regression or the CNN. And the user only participates in either selecting the model or in providing the input data, and then it just brings out the results that they needed. So we have transparency, we have simplicity, and we have control over which model is required for the results that you want. Data processing, as I said, we both had different data sets. One was a textual data set and the other was an image data set. The breast cancer data set was the textual one, so that required some cleaning with the values, normalization, making sure that we don't have any repeated values, any empty values, or anything of the sort. And then we had to split it into a train and test split. For the brain cancer, we used MRI images where we needed to resize the images, make sure that they're all normalized and they're all following the same patterns and rules, and some minor augmentation in order to have the data clean for the models or the networks to be able to train efficiently on them. Yeah, so as I was saying, the model, we were training these models. So for the logistic regression, we're using just supervised logistic regression learning. There's nothing to it. I set the max iteration for it to be 2000. We don't have any epochs because, again, this is just a logistic regression. It's just linear. And we're using the full batch size for the entire training of the module, and then we test later on. Basically, we got an accuracy of 96.49, which I believe is pretty good. For the convoluted neural network, which is a little more complicated because it's using pictures, we're using supervised deep learning. We have different images, and each image comes with its own class. We have multi-class image classification, 25 epochs. Abu Bakr used a batch size of 32, and he ended up getting an accuracy of 83.94, which also is pretty amazing. Here you can see pictures of our matrices and some of the scores that we have. So the breast cancer module, we have an accuracy, as I said, of 96.49. Our precision is 0.97, which is almost 98%, a recall of 92.86%. 92.86%, and then F1 score of 95. And then similarly, on the other side, for the brain tumor model, we have an accuracy of 85%, a precision of 86%. Our recall score came out to 85%, an F1 score of 85. And because this is a convoluted network, we had, because there was a specific batch size used, we had a test loss of only 36%, which I believe is pretty good. Yeah, and then we have some pictures to show the system, to demonstrate how the system was actually working on our interface, on the user interface, where you can see both of them here. Our code is also provided. There is a link for the GitHub. We've given running instructions as well for you to be able to run the code. Yeah, we have some limitations. Obviously, the data sets were limited. I think there was only maybe like 500 input points for the training of the breast cancer, and I think around 80 to 100 images for the brain tumor, or I think we added a little more afterwards. Yeah, so obviously there will always be limitations with data sets, with the cleaning of the data sets, the quality of the data sets, and the amount. If we had larger data sets that were confirmed, we would obviously be able to create more accurate and more precise models for our hybrid system here. Another issue is that it does require a proper input if the user is going to be putting in their own data. They will also need to be able to clean it in the proper way in order for the models to be able to read it the same way, which is why we added user instructions. Um, yeah, and obviously it's based on AI. It's based on machine learning. Medical predictions are actually probabilities. Um, I do not believe that we will be able to reach 100% as of right now where we are with technology. That being said, I believe we are on a good track, and we do have a model that does provide a high accuracy. Uh, that being said, it is not a replacement for medical professionals. And obviously, we have the ethical considerations, patient privacy. There's a lot of data being inputted to train, there's a lot of data being inputted to get the output and the predictions. So we need to be ethically aware of our patients' privacy when we are handling their data. Same goes with data protection, human oversight. That's a little. Those are some of the issues that we can have when we're cleaning the data, when we're inputting the data, or when we're even collecting the data. Yeah, and obviously, as this is AI, we would love to have it be used as responsibly as possible, because these are patients' lives that we are handling here. And for future improvement, we would love for the user to be able to get an automatic recommendation of the model that they're being used, whether they input the data and then the system is able to detect what kind of data that they're inputting, what kind of cancer that they're trying to predict, and then move them on through there rather than it being manual. Also, our system is the user interface, as nice and as amazing as it is. It would help to have some visualizations to be able to explain how the AI is able to come up with these results based on the data that it's given. As I've mentioned before, also larger data sets would help a lot to be able to create a more precise and a more accurate system. Yeah, and then also we would love to be able to deploy this and add more disease support, as we're only looking at two different cancers right now, so a little bit more would be nice. So yeah, as a conclusion, I believe we did what we set out to do. We created a very simple system that anybody is able to use, given that they have the correct data that is cleaned up correctly for them or by them. So yeah, it's a simple system. It's able to detect with high accuracy what the type of brain cancer, or whether it is malignant or benign. Um, yeah. So I hope you guys have enjoyed. Thank you very much for watching and listening. Here are some of the links at the very end of the presentation where you can see the original data sets before we actually clean them. And you can see the repository where our code is in case you wanted to run it yourself. Thank you very much.